presentation, we take up a topic Arenes and Aromaticity of Organic Chemistry course CH102. Arenes is a common name for benzene and its derivatives. Now today's lecture include what are the organic compounds, classification of organic compounds, aromatic compounds, and aromatic compound include benzene, structure of benzene, stability of benzene ring, properties of benzene. Now, you people must be knowing what are organic compounds. Organic compounds are the compounds that contain carbon. Now, broad classification of these organic compounds includes two classes, aliphatic and aromatic compounds. Aliphatic further subdivided into two categories, open chain and alicyclic. Alicyclic means aliphatic cyclic. The cyclic compounds which resembles aliphatic in nature like cycloalkane, cyclobutane, cyclopropane, etc. In aromatic further subdivided into two categories, one is benzene and its derivatives and other one is other aromatic compounds which are not benzenoid compounds. Now today we discuss about the aromatic compounds, and in aromatic we discuss benzene and its derivatives. Now how this benzene is isolated? The benzene was first isolated in 1825 by Michael Faraday. He extracted it from the whale oil. The whale oil at that time was used to produce a gas which was used to illuminate buildings in London. Many other compounds then discovered in 19th century and which are related to benzene. All these compounds have a common phenomena, all have a pleasant aroma, because most of these compounds at that time were isolated from plants and trees. That is why these are known as aromatic compounds. All these compounds have certain common properties. All these compounds have low hydrogen to carbon ratio. These are unusually more stable, and these all show some special properties which are known as aromatic properties. Now we come to the structure of benzene. From elemental analysis and molecular weight determination, the molecular formula of benzene is C6H6, means it is having 6 carbons and 6 hydrogen. Now next question is how these atoms are arranged in benzene. There are 5 possibilities to arrange these 6 carbons and 6 hydrogen. First formula number 1, that was given by Kekule in 1858. It is a 6-membered cyclic compound. It is having a conjugate double bonds. Second one is a Dewar formula. It is a bicyclic ring system and it is having 2 double bonds. And third one, it is a 5-membered cyclic compound having 2 double bonds in the ring and 1 exocyclic. Now fourth and fifth, these are aliphatic compounds and this contains a straight chain carbon, and these are unsaturated compounds corresponding to the formula C6H6. Now the next question is, out of these which one is the structure for benzene? So we can establish the structure on the basis of certain experimental facts. Number 1, it was found that benzene produces only one monosubstituted product. On bromination, it gives only one bromobenzene. On chlorination, it gives only one chlorobenzene. On nitration, it gives only one nitrobenzene. That means all the hydrogen in benzene are equivalent, so that replacement of any one hydrogen gives the same mono-substituted product. So, now we see, come back to the structure, in which structure we have all the hydrogen equivalent. So, in structure number 1, we have all the equivalent hydrogens. In structure number 2, we have 2 types of hydrogens. So, from this structure we should get 2 types of mono-substituted product. In structure number 3, we again have 2 types of hydrogens. So, again it will give 2 type of mono-substituted product. In structure 4, we have 1 type of hydrogens only, CH3. In structure number 5, we have 2 types of hydrogens, CH2 and CH. So, again structure number 5 gives 2 types of mono-substituted product. So, depending upon our experimental fact, we can reject structure number 2, structure number 3 and structure number 5, and we are left only with structure number 1 and structure number 4. Now, out of these, which one is our benzene? So, now next experimental fact, benzene forms 3 isomeric di-substituted products. So, again come back to the structure. So, we have only possibilities 1 and 5th. Now, 1 we can have 1,2, we can have 1,3 di-substituted, we can have 1,4 di-substituted. Here 1,2 and 1,3. So, again now we have 3 types of di-substituted product with formula number 1. Now, we come to formula number 4. Here we have 1, 1,6 and 1,1, only 2 types of di-substituted products. So, structure number 4 must be rejected according to this experimental fact. So, we are left only with structure 1. So, structure 1 can give these 3 products on bromination, 1,2-dibromobenzene, 1,3-dibromobenzene and 1,4-dibromobenzene. But further, there are 2 possible 1,2-dibromo products. Here these 1,2, these 2 bromine are attached to these 2 carbons which are attached through double bond. But in this form, the 2 bromine are attached to these 2 carbon which are attached to through only a single bond. So, now we have 2 possible structures for 1,2-dibromo product. So, in total we should get 4 di-substituted products. Now, according to Kakule, the 2 possible structures of benzene which differ only in arrangement of double bonds here and here. Now, you see this is double, this is a single. So, this is only differ in arrangement of double bonds. These 2 are in rapid equilibrium with each other, so that this could not be separated. And similarly with 1,2-dibromobenzene also, these 2 possible 1,2-dibromobenzene, these are in a rapid equilibrium with each other. So, that is why in experimental we obtain only 3 di-substituted products, not 4. Further evidences came from X-ray analysis, which gives the bond lengths. So, X-ray studies of benzene shows that all the 6 carbon-carbon bonds in benzene are equal, and the bond length is 1.39 angstrom, and this bond length is in between a carbon-carbon single bond length which is 1.53 angstrom and a double bond length which is 1.34 angstrom. So, this indicates that these 6 bond lengths are in between single and double bond lengths. So, how we can adjust this finding? So, this can be adjusted if we consider benzene is a resonance hybrid of 2 Kakule structure. So, these 2 structures are in resonance with each other. So, we can represent a resonance hybrid like this. So, from this it comes to conclusions that all the bonds have slightly double bond character. So, in alkenes, double bond is localized between two carbons, but now in benzene, double bond is not localized between two carbons and all bonds have a double bond character. So, this makes the difference between benzene and alkenes. Now, better we can understand all this by taking the orbital picture of benzene. Benzene is a planar molecule. Each carbon is sp2 hybridized and each carbon is having one unhybridized p orbital with one electron. So, in total we have 6 p orbitals with 6 electrons, and these all, because all these are planar, so there is a perfect overlapping of these p orbitals and formation of two donut shaped electron cloud. So, this is these are p orbitals and there is a overlapping of these p orbitals and this is two donut shaped electron cloud get formed, one above and other below the benzene ring. And this delocalization of electron gives a special feature to the benzene ring, that is stability. So, now we will discuss the stability of benzene ring. For this we take the experimental data of heat of hydrogenation. You must be knowing what is heat of hydrogenation. It is a heat evolved when an unsaturated compound is reacted with hydrogen to give a saturated compound. So, if we take the simple alkene with one double bond and react with hydrogen, it gives the aliphatic compound, and the heat of hydrogenation here for one double bond is minus 28.6 kilocalorie per mole. Now, we take the cyclic compound with one double bond, it is a cyclohexene. It gives on hydrogenation cyclohexane and again it consumes minus 28.6 kilocalorie per mole. Now, if we take two double bonds in a ring which takes 2 moles of hydrogen to give you cyclohexane, and it was found that the quantity is exactly the double of which is evolved for one double bond, here it is a double, that is minus 57.2 kilocalorie per mole. So, if benzene is having in a cycle 3 double bonds and on hydrogenation it consumes 3 moles of hydrogen to give cyclohexane. So, it should have a calculated heat of hydrogenation at thrice the value of a ring containing only one, that is cyclohexane, and the value should be minus 85.8 kilocalorie per mole. But it was observed that the heat of hydrogenation is very less from the expected amount, and that is minus 49.8 kilocalorie per mole. So, it leaves the difference of 36 kilocalorie per mole. So, what is this energy? What is this difference? This difference of energy which is between the actual molecule is our hypothetical cyclohexatriene, and that of the resonance structure of benzene, that is known as resonance energy, and this resonance energy for benzene is 36 kilocalorie, or we can say benzene is more stable than cyclohexatriene by 36 kilocalorie. Further, it is even more stable than cyclohexadiene. Now, you can see this is energy of for hydrogenation of benzene is minus 49 and for cyclohexadiene it is minus 57. So, that means benzene is even more stable than cyclohexadiene by 24 kilojoule per mole. So, this stability of benzene reflects on its reactions. That is why benzene undergo a special set of a reaction. As such, it is an unsaturated compound, and like other unsaturated compounds like alkene and alkynes, it must undergo electrophilic addition reactions. But it was observed that instead of addition reactions, benzene undergoes substitution reactions. For example, on reaction with bromine, it gives bromobenzene, not 1,2-dibromocyclohexadiene. Now, why? The reason is, as we discussed earlier, because benzene is more stable ring, so and on addition it gives cyclohexadiene, which is less stable than benzene. So, that is why it prefers to give, or it prefers to retain its benzene character, not to cyclohexadiene, and that is why it gives bromobenzene, not not a addition product, that is 1,2-dibromocyclohexadiene, or we can say addition reaction destroys the delocalized benzene structure, which is the main key for a stability of benzene ring. Further, we can see in other reactions also. On reaction with, on nitration, it gives, benzene gives nitrobenzene. On sulfonation, benzene gives benzene sulfonic acid. On reaction with alkyl halide, gives alkyl benzene. On reaction with acyl chlorides, it gives corresponding ketones. So, in all these, benzene gives a substituted product, and these products and these reactions we will discuss later on. Now, stability not only affects a course of a reaction, it also affects the reactivity. Due to this stability of benzene, it becomes a slow, or it do not react under the conditions in which alkenes react very fast. For example, we take the alkene and we react with bromine in CCl4 and we get the addition product 1,2-dibromo product. On reaction with aqueous KMnO4, the KMnO4 color decolorizes and corresponding diol get formed, which is again an addition product. Here in case of bromine also, the color of bromine decolorizes. But if same reaction we perform with benzene, with bromine CCl4, there is no decolorization of color. With KMnO4, aqueous KMnO4, again there is no decolorization of color, means benzene do not react under these conditions in which alkene react very fast. So, again reason is same, its delocalized structure which gives a stability to the benzene ring. In alkenes, double bond is localized, but in benzene double bond is not localized. So, it undergo a reaction with bromine only in presence of a Lewis acid ferric bromide. So, ferric bromide helps in generation of a electrophile, and once the electrophile generated, then only it react with benzene and gives a substituted product bromobenzene. So, the reason here the same, delocalized structure of benzene and which gives a stability to the ring, and that is why its reactivity becomes poor as compared to alkenes. Now, we can summarize today's presentation. We have discussed benzene is a 6-membered ring with 3 delocalized pi bonds. It is more stable than the hypothetical cyclohexatriene, and due to this stability, it undergoes electrophilic substitution, not addition reaction, and it is less reactive than alkenes. In the next presentation, we will discuss about the other aromatic compounds than benzene. These are different from benzene, but resembles benzene in their properties. That is a special feature which make them similar to benzene. So, we will see what are those properties and how these compounds are similar to benzene, and further we will discuss about benzene and its derivatives, their nomenclature. Thank you.